Okay. So optimization problems are really cool. It's just like one of the things that I think is kind of one of the culminating topics of calculus, in our version of calculus at least, because we're really building up to this, and everything we've been doing has been placing a block on top of the last thing, and we're just keep using it to move forward, right? So we like talk about limits. We use limits to talk about derivatives. We use derivatives to find maxes and mins. And now we're going to think about maxes and mins in the context of real world applicable problems. So I hope that's exciting to you. That's sort of like, you know, the point of this class for a lot of people is not necessarily learning the math, but thinking about what's applicable to your own field, right? And so let's talk about optimization. And this first part, this sort of part that's on the screen right now, is supposed to motivate you to think about why we care about this, right? So optimizing something, when you think about the word optimization, hopefully you think of the word optimize. And so when you think of optimize, I think most people would think, oh, we're trying to get the most out of something, right? Trying to optimize. And that's the idea behind here. And getting the most out of something is really, really common in every single field. It doesn't matter whether you're, an investor trying to get the most out of your investments, or a conservationist who's trying to get the most out of the species, right? Have the most diverse species, for example, or maybe we're in disease, we're in the COVID business, right? We're trying to minimize COVID, or trying to reduce COVID. Minimizing something is also an optimal thing if you want it to be as small as possible. And so what I tried to do here is just give a couple examples. What I have 6 bullet points here that sort of talk about different possible scenarios. And I hope one of them relates to you, and or you can relate to one of these examples. But I also hope that you can think of your own example that might be interesting for your own field. And so as we go through here, I would like to box in a few things. I'm going to box in green things that are constraints, and I'm going to box things in blue that are things we want to optimize. And what I'm trying to say when I write those two things down is, in most situations, you want to get the most out of something, but you have some constraint associated. So back to my previous examples, you want to maximize your profits in an investment, but you only have so much money to invest, right? So the constraint there would be the money. You want to minimize disease in the region, but you only have so much influence over people's behavior, right? So you're sort of constrained by people's behavior. And so in each one of these examples, there's something we want to maximize, but something that's constraining us. So the first example says, what are the light levels or nutrients potentially that yield the best crops, right? So getting the best crops is a maximization thing. We want to maximize the crop output. This is something farmers think about all the time, right? They're trying to maximize their crops. They may not be using math behind it, but a lot of people do, or they're at least guided by mathematics. But the idea is you only have so much light or so many nutrients, right? So the amount of light or nutrients is actually a constraint on the best crops. And this is actually the first example. If we kind of just allow me to slide down to the next page, the very first example we'll look at is a function that tells us crop output given nitrogen level. And so that's exactly the kind of thing I'm talking about. Okay, a really common question is like, how do we get our products out to the distributors? And so this is a general sort of topic that's known as logistics. I don't know if you've heard of that field. It's actually a field itself. Some big colleges and universities have logistic departments that sort of focus on these kind of questions. Really common example I've heard of in mathematics is, you own McDonald's or some store where there's a bunch of your sort of sub stores or different chain locations throughout the country, and you have to get your product to all these places, right? Your hamburgers need to be at every McDonald's or something. How do what roads do you take, or in what order do you sort of deliver things to each one of those locations to maximize your output? So you want to like minimize the amount of gas you are spending, also minimize the time you're spending around there, which is ultimately going to maximize your output. So anyway, that's sort of a general idea behind logistics. And I'll just sort of plug my own class. Math, I think it's 4,400 next semester. studies these kind of problems and some of the math that you can use to answer those kind of problems. Okay, the next example I put down there was like, oh, you only have so many supplies, but we want to make, sorry, given a limited amount of supplies, how can we make the most effective or the most cost efficient or the largest product, right? So each one of the things on the end there, so either most cost effective, efficient, largest, each one of those things is like a maximization thing, right? Or at least an optimization thing. But oftentimes you're limited by what you have, right? You have a limited quantity of supplies. We see an example like this in a couple pages. Let me just go ahead and show you that one. This is an example where we're trying to build some amount of, or trying to build the biggest fence possible, but we only have so much fencing. And so we have some conditions we're trying to maximize, but we're constrained by our material. So we'll look at one like that in this one. Okay, this is one I always come back to, like the dosage or frequency of a drug, right? We want to effectively fight disease. And so fighting the disease would be the thing we're trying to minimize. We want to minimize disease, but we don't want to hurt the patient, right? And so hurting the patient is something we need to be careful about. In other words, if someone has a disease, we could oftentimes blast it out of them or something, but you might kill the patient in the process. So that's actually a constraint to think about, hopefully, obviously. Or the second part of there, or the patient becoming broke. Maybe there's really good methods to doing things, but people can't afford it, right? So those two things would be constraints. All right, the next bullet point is my favorite one. I know people are constantly trying to calculate this in their head. And in reality, we're all trying to do that, right? What's the least amount of effort I can put into Math 2300 while still getting the grade I want, right? So you're trying to minimize effort, but you could just do nothing, of course, but you'll fail the course, right? And so you still want to get the grade that you want. So that would be a constraint. And that's kind of I know this is kind of a joke one, but it's in reality, it's true, right? You're all distributing your effort over your classes and you're sort of calculating in your head the best way to do that while still maintaining whatever your grades you want to be. And oftentimes we devote more time to one class than another one. I will preach. Thank you, Josh. But in reality, we're not using equations, but that is something you're considering. Okay. And what I think about in my own research is sort of the last example. I do many different things, but one of the things I think about is we want to limit some sort of invasive pest, but we only have so much money, right? So we want to limit some population. That would be a minimization thing, but we're constrained by our funds. So that's a really typical kind of thing that we want to do, that mathematics provides us with the tools to approach. So hopefully these give you an idea of the kind of questions we'll ask. You'll see a few of them in practice. We'll do some homework exercises related to this. This homework is due next week, so don't freak out too much about it. Not on the test, of course. But this is ultimately what we've been building towards, right? Answering these kind of questions. Any thoughts or anything about anything? Anyone thinking about one in their own head about something that popped in their mind, something they're familiar with or curious about? Just wondering if you've been inspired. Anything?
I used to take chemistry, and it kind of reminds me of limited reactants and stuff.
What happens with that? So I'm not familiar with. You say limited reactants. What happens there?
Yeah, it's like when you want to optimize the most product, you got to find the limiting reactant, and that's most of the constraint.
Yeah, that sounds like it would be applicable, and it's interesting you mentioned chemistry, because when I think of chemistry, when I used to think of chemistry, I used to think it had nothing to do with math. But then when I started knowing chemists more deeply, they actually use more mathematics than a lot of the other sciences. When you go really deep into chemistry, it's like all linear algebra and physics and things like that, which is kind of cool to think about. So yeah, that problem, and I don't know if you looked at it from a mathematical standpoint, but there probably is a mathematical approach to that, like using calculus, for example. Yeah, that's a good one. Any other ideas or things you were thinking about? Applications of this kind of thing? All right, well, maybe some of the examples will kind of inspire you, or at least show you how this can be used. And hopefully you can sort of see that, hey, we're in calculus, right? And calculus, just this paragraph I'm highlighting, we find maximum minimums in calculus. So if we want to optimize something, which usually means finding a max or a min, then we can do that with calc. Now we need an equation, right? So that what separates things from, I don't know, like what Josh was saying in a chemistry situation. Yes, there's probably some equation that sort of underlies that, but until we have calculus, we usually don't see those equations. And so in other words, you can use your calculus now to look at things more deeply with equations. Anyway, let's look at sort of the general steps. And so this is the thing that people always get tripped up on, right? All the optimization problems are a little bit different. And if you just page through the next couple of pages, they're very different flavors. And you might, if you just sort of compared the questions separately, you might not even realize they're the same topic. Now that's fun and exciting because we're actually doing real world stuff here, but it can also make things a little tricky. And so to try to help with these things, I've listed some guidelines to follow when you're doing these problems. But the thing is important to note, maybe just right off the bat, is that some steps aren't going to apply. So these are just general things to look at, but if you don't apply one of them, it's okay because it may not apply. So some steps don't always apply. Like, for example, you can see it says drawing a picture, if applicable. Sometimes drawing a picture just doesn't make sense. Oftentimes it really does help, but if it doesn't make sense, then don't do it. That's the kind of thing I mean. And the other thing I'll say is some of the steps might apply, but they've sometimes been done for you. And so sometimes a few of the steps will have been done for you. And so the first couple of examples are these kind of examples where we're not actually doing steps 1, 2, 3, 4, for example, and we're just kind of maximizing something. But the third example and the fourth example is where we really start to get into things, but we won't see that till next week. My goal here is to get through the first two examples. Just make sure that's right. First two examples. See how far the first two examples take us. Yeah, just the next page. Okay, so let me just sort of briefly look at each one of the steps just very quickly while we look at the next example. So I'll go through each one of these things. Maybe I'll just slide up a little bit so we can see all this stuff on the same page. There we go. So like I said, right, the first example is we have some function here, y, and it tells us the yield of a crop. So it tells us the amount of crop that's outputted given n, which is nitrogen level, right? So you plug in a nitrogen level, it tells you how much crop is outputted. And the question is, what nitrogen level yields the most crop? And so, as I mentioned, this is one of the ones where most of the steps are done for you. And so let's just look at the steps and see that they're done, right? So the first step says, let's define the key variables. The variables have already been defined, right? Y is crop yield, N is nitrogen level. So we don't have to do anything tricky there. Draw a picture. Not really applicable here, although I will graph it. Derive the objective function. Already done. Y is the objective function. And so we don't even have to do those kind of steps. Kind of looking forward, this is the kind of problem, if you wanted to read this one later, this is the kind of problem where we need to do like all the steps, right? You don't see an equation there, for example, there's no variables being defined. And so this is the kind of problem where we're going to take it a step further. So question, parts 1, 2, and 3 are done. We can think about constraints on this one. Number 5 is already done. It's already in terms of one variable. We'll do number 6. We'll do number 7, right? So really all we're doing is 4, 6, and 7 in this problem because most of the things are already done. And so I'm just going to make that note at the top of the page here. Examples on this page in particular have most steps done for you. Again, kind of taking a baby step a little bit. Not that it's the easiest thing in the world, but not jumping right into the hard ones, right? And so, for example, on this one, I'll just say only need to do steps, what did I say? 4, 6, and 7. The other ones are either done or they don't really apply. Okay, you kind of see the setup there, the questions about the steps. The steps will come into more play and be more important when we see one of the more complicated examples. But thoughts about any of that? Anything to clarify so far? All right. Let's graph this thing. It's always a good idea to graph it. I graphed it ahead of time. And here's what this y function looks like. It kind of does a funky thing. It does this. Oops, that's not quite right. It does this, goes through the origin, and does this. And so it's got like a max on the right side and the positive values. So these are the n values. And then the output is on the y-axis, which is the y, right? It's a crop output. And so I wanted to look at that because it has a max and a min, right? We're trying to get the most out of these crops. And so we're really looking for the max. And hopefully that makes sense. So kind of like looking at what yields the most crops, what that's saying is we want to find the nitrogen level, which I'll call n star. Oftentimes we represent like critical points with a star or something like that. So we're going to find the critical point n star such that what is this label? Such that y of n is maximized at n star, right? i.e., find the max. That's what I'm trying to say. And we can see it's there in the picture. I didn't label any of the axes, but we can see it has one. Does that make sense? That's what this question is trying to ask us? And when we're looking at the picture, there's going to be two critical points, right? So we're going to find critical points, right? Because we want to find the max. And so there's two of them. There's a max and a min. And the min is over on the left side. In other words, negative nitrogen levels would produce that min. And so that doesn't make sense, right? And so that's where the constraints come in. Right, that's step 4 that I said we should consider about this. We can consider the strains. Constraints, let me spell it right. Right, we can't have negative nitrogen. And we also can't have negative crop output. And so most of that graph is irrelevant. The only real part of the graph we care about is this part. Because that's positive nitrogen, positive crop output. Over here is mathematically relevant, but practically or biologically irrelevant, right? Negative nitrogen levels, negative crop output. Doesn't make any sense. And so that's, worth thinking about, because when we find a couple of critical points, one of them is going to be meaningless, right? So the constraints are we need the crop output to be not negative, and we need nitrogen levels to not be negative. Oops. Again, just looking at the first quadrant is what that means. That's super typical in real world applications is we most of the time just care about the positive parts. Sometimes the negative part makes sense, but a lot of times the negative parts don't. With me? Seems okay? All right, so we want to find the max, right? So we're going to find the critical points by taking a derivative. This is the kind of thing that should be a good review for the test Friday. I'm going to ask you to do this kind of stuff with functions that look kind of like this. This is not that complicated of a function, right? Yes, it's a quotient rule, but there's polynomials in there, and the derivative's not that bad. And so this is the kind of thing that hopefully makes sense. And if it doesn't, this is a good time to ask a question about it, right? So it's a quotient rule. So it'd be, so we're taking the derivative. So it'd be f prime g minus f g prime all over g squared. And we can simplify that down. That simplifies down into 1 minus n squared on the top, on the numerator. Right, and we want that to be 0. So let me just sort of pause there and see if that looks okay. This is a 2n, and the 2 is a little bit funky. Let me rewrite that part. Right, you'll have n squared minus 2n squared, which gives you the minus n squared. Let me know if that looks okay. And we want it to be 0 because we're trying to look for the critical points, right? Sorry. I get this in here. I thought that was just attached there. Go back in there. That derivative look okay? I would love to answer a question about it, right? This is the kind of thing I'm going to ask you to do on Friday in the test. That derivative, that is. All right, well, if we want the derivative to be 0 and it's a fraction, we want the numerator to be 0, right? So we talked about this last time as well. The derivative will be 0 if the top is 0. And that means that we need 1 to equal n squared, take a square root, and we get n equals plus or minus 1. All right, so I'm going to label the graph there then. What we just found, probably the max is that place at 1, and the min is probably over there at -1, right? So I just labeled the graph. I know it's one of the bad things about doing this online is you can't see where my hand is on the paper and stuff just pops up. So anyway, I just labeled the graph with those 2 points. We're going to verify that we did find the max, but you know, just looking at the picture, it's probably at 1. And -1 is outside of our constraint, where we just said that the constraint is that we need to have positive n values. So it doesn't n equal -1 doesn't make any sense. And so we can just go ahead and throw that one right out. Right? N equals -1 outside the constraints. And so ignore it. Okay. And then we can verify that we found a max using one of the tests. Sorry, that constraints looks terrible there. Let me rewrite that a little bit better. But, you know, unless we did something wrong, 1 is going to be the... Okay, so let's use the first derivative test. So I'm going to verify n equals 1 is a max. I'm going to use the first derivative test. There's no reason we have to use that. We could use a second derivative test, right? The answer, the point of these problems is just figure out the answer. We're not being told what to do. And so let's go ahead and do that right here. Just make a little box. We'll do it right here, right? We test x values in the derivative. Except they're n values, sorry. They're n values in the derivative. And so we're testing points around 1. So let's plug something in to the left of 1, like 0, and something to the right of 1, like 2. And we put them into the derivative because that tells us increasing, decreasing. Right? When you plug a 0 in there, you get a 1. That's a positive number, which means increasing. When you plug a 1 in, you get 0, flat. When you plug a 2 in there, you get a negative number, decreasing. All right, this is the first derivative test. Increasing, flat, decreasing. Increasing, flat, decreasing is a max. How does that look?
So is the final answer now 1 because that's when it would yield the most crops?
Yeah, so I want to review sort of what we were trying to figure out here in just a second. That's exactly the question we should be asking. But is the math okay? Or the questions about the algebra anything before we kind of punch it home. I'm going to write one more thing down and I'll out of room here. Questions about the process at all first? Okay. I'm going to have to zoom into my tiny blank space there. So hopefully you've got a little space you can write this. But remember, the question was, what is the nitrogen level that yields the most crops? And so I'm going to write the answer, sort of the final answer right here. I do apologize again that we're running out of space, but the idea is N equals 1 yields the most crops. But if we wanted to know the most crops yielded, we plug that into the function, right? So that's one thing we learned. The other thing we learned is y of 1 would tell us what the most crops are. That would be 1 over 1 plus 1 squared, which is 1/2, is the amount of crops yielded. Apologize that you got a little bit crunched in there, but those are sort of the takeaways of the problem. And we're not really told what y is measured, and I was just trying to check that. It just says the yield of the crop. So maybe it's in like tons or something like that, and half means half a ton or something. Not really sure, but depends on what the units of y would be. I'm assuming it's not number of crops, though. I'm assuming it's not like half a crop. Things like that are usually measured in like truckloads or something like that. All we're doing is finding a max, though, really, and we're finding a max and interpreting it in the context of our problem. And it's literally nothing we haven't done. It's the exact kind of thing that the test is going to be on. We're just doing it with an application in mind. Questions at all?
All right. So essentially we were looking for the max, right?
We were looking for the max, right? What nitrogen level yielded the most crops?
Yep.
Y tells us crops. So if we want the most crops, we're maximizing that function.
So the first thing we did was found the first derivative, right?
Correct. Yep.
And then the next thing we did was we set it to 0, and then
Yep.
that way we found the critical points, right?
Correct. Those are the critical points. And
then
in that
from
case,
there,
that was the max and the min, right? If you just looked at the picture, it's like the peak and the trough there. Yep. Keep
Yep.
going.
And then from there, we used the first derivative test to find it. And
so, you know, the idea is we can't rely on this picture. I like drawing the picture because it's I hope you agree it's helpful. We see the answer, we verify what we write down is true. But the idea is we shouldn't need the picture, and we should be able to write all this stuff down without it. And so if we found n equals 1 without looking at the picture, we wouldn't know if it was a max or a min. It might be a min, might be an inflection point. And so this part right here is the first derivative. Oops, I hate when that happens. Is the first derivative test showing that we actually did find a max. Just kind of relying on things that we've been learning to say, okay, not only is this a critical point, but it's a max using the first derivative test. And I'm just sort of saying, okay, we're sort of cheating in some sense by looking at the picture. It's cheating if you just write a picture down and that's your answer, right? That's what I would consider sort of not doing the question correctly. Looking at a picture to support your calculus is a nice thing, in my opinion. Anyway, does that clarify?
Because we knew it, so we'd have to test both of them in order to give us the right answer.
Yeah, and we just ignored the one on the left because I don't even care what n equals -1 is, because it's a meaningless thing. Like, has nothing to do with this problem, right? So,
all right. Thank you.
Other questions? Other things? I didn't actually check to see, or haven't yet checked to see how the homework went on Monday. So I'm assuming it went okay based on there not being questions, but let me know again. Test on Friday. Would love to clarify any of this stuff. And we can spend a good half hour, I think, on review and those kind of things, but I would like to look at this next one. It's pretty much the same idea. So hopefully if that one didn't make sense, this one will drive it home a little bit. So it's the same kind of problem, just a different context. So in this context, C is telling us the concentration of some drug in the bloodstream. So we're ingesting something, and then T tells us hours after ingestion. And so it tells us like over time how much is in your body. Right? When you like take aspirin, it doesn't go right into your bloodstream, it sort of gets absorbed over time. And so it's the same kind of problem where we don't have to do most of the steps. We're going to do the same steps we just did last time. We're going to find the max, think about constraints, interpret our answer. And so, yeah, let's just do that. It's very similar, so we don't have to spend too much time in it. We have the same constraints. C has to be not negative, and T has to be not negative, right? Concentrations can't be negative. Time can't be negative. And so we're kind of focusing in on the first quadrant again. Actually forgot to graph this one ahead of time, so let me go ahead and do that real quick, just so we can look at the answer as we're doing it. And we can plot it right over here. It actually looks very similar to the last one. That's interesting. Well, I guess they're both rational functions, so it's not that interesting. They're actually very similar functions. It's not even worth drawing. Anyway, it's very similar, actually. It looks just like this one. Not all functions look like that. Okay, but the same kind of thing. Well, looks like we'll probably get 2 critical points. One of them is going to be irrelevant because it'll be negative. We'll just sort of verify that we've got the max, right? And so the question here is, what's the highest concentration that the blood will ever get? Okay, that's a relevant thing. If it's, if it's like a deadly drug or something, you don't want it to get too high, for example, or if it's you need a certain amount in your bloodstream for it to work, that's important. So when's it going to get there? So, it's a relevant question. So just to be clear, the highest concentration means we want to find the max of C of T. Right, find the highest concentration. So we'll take another derivative, another quotient rule, and a not too bad quotient rule. F prime G minus F G prime all over G squared. And we want that to be 0, right? So we want to simplify that a little bit and then set the top equal to 0. And so when you simplify it, it ends up being 12 minus 12t squared plus 6 on the numerator. I'll rewrite the bottom, but the bottom doesn't really come into play that much, right? Because we want this to be 0, it just has to do with the top. And so we take the top and set it equal to 0. Looks like my iPad is lagging a little bit. Let me just hold on there. Okay. And this is not a hard problem, right? So we just subtract 6 divided by 12. We'll get t squared equals 1/2. Take a square root, and we get our 2 answers, plus or minus square root of 1/2. And so we can go ahead and just label those right up there. It's probably plus square root of 1/2 and minus square root of 1/2. But we'll verify it just to be sure. And just to kind of be clear, in theory, we might find multiple positive ones. And if we found multiple positive ones, to John's question before, that's when this classifying them is really important. Right? It's possible that we have a function that kind of does this thing over here. And if we're trying to find the max, the question is, we'd have 3 critical points, and classifying them would be particularly important. We're just looking at sort of quote unquote easy ones right now that only have 1, but in practice there could be more than 1. All right, seems okay. And so we're going to ignore the -1 again because we need t to be positive or non-negative. And so we're just going to classify the positive one. And I'll use the first derivative test again.
Are there ever going to be a situation where when you set the top equal to 0, the bottom might equal 0, making the problem like have to be solved a different way?
So if that were the case, that would imply that the derivative would be undefined at that location, which would mean it would be a discontinuity. So no, the top and the bottom can't be both 0 at the same time. It's possible that the bottom would be 0, which would be a discontinuity, or the top would be 0, which would be a flat point. But unless I'm mistaken, I don't think they can both be 0. I'll have to think about that a little bit. That would be like a real special case, because that would imply some kind of discontinuity, kind of really funky one. Right? We saw that when we looked at limits. That happens in limits, but I don't think it happens in the normal function. Let me think about that again, maybe get back to you, but I don't think that's possible.
Thank you.
Let me think about that a little bit more. Other thoughts like that? That's a good question. I like thinkers like that. All right, let's just classify it real quick. So I'm going to do the same thing here. Let's see, we have t values, and we're plugging them into C prime. And square root of 1/2 is in the middle. Something less than it would be 0, and something bigger than it would be 1, right? So those are nice, easy numbers to plug in. Sorry, again, I got kind of crammed there, but when you plug in 0, you get a positive number. When you plug in square root of 1/2, you get 0. And then 1, you get a negative number. And so we have increasing, flat, decreasing, and so this is a max. We knew it was looking at the picture, et cetera, but we've just verified it. All right, so the max concentration occurs really soon after ingesting it, or I don't know, square root of 1/2 hours. I don't know what square root of 1/2 is, but less than an hour, right? So it happens less than an hour. And if you want to know what the max concentration is, you plug that into the function. Right, this just tells you the location it happens. If you want to know the concentration, you plug that into the original function. And I did that beforehand, and I got approximately 2.12. Just trying to drive home the 2 types of question. Right, which one is the answer to the question that was posed? Let's evaluate that, right? What is the question that was actually asked? Thoughts? Which one of those is answering that question?
It would be 2.12, right?
Yeah, right. So this question, what is the highest concentration? This is the highest concentration, which is different than what we looked on the last one, just to kind of clarify that, right? If we looked at the last one, the question was, what nitrogen level yields the most crops? And so that was the critical point. So it depends on what the question is. This one wanted you to plug it into the function, and that would be the answer. Okay. Again, this is just kind of setting up the idea, right? We're given the function, we're literally just maximizing something, finding critical points, which is exactly what we've been doing for the last couple of weeks. Now, I wrote down these general steps that we should think about when we're working on these problems. Let me get this tool out. But we haven't used them yet. And so today is going to be the first day where we actually hone in on these steps right? Because it says on the right here, sometimes you don't use these steps. And in the first couple examples we saw, we didn't use them. But we're going to use them moving forward, right? So let's just remind ourselves of the examples we already did. The reason we didn't use any of the steps because most of them had been done for us, right? We were given a function in this example, and we were asked, what is the max of it basically? What's the max cropped output? And so we found the max. And that's nothing that, is different than what you did on the test, for example. It was just taking a derivative, setting it equal to 0, right? That's how we find the max. And then we just classified it using the first derivative test. So, if you remember back, we looked at this back a week ago or last Wednesday, we sort of used this as a way to review for the test because we weren't doing anything different. We were just kind of finding the max with an application in mind, right? Same thing with the second example. But now we're moving into some problems that require us to think a little bit more carefully about what's going on and to follow the steps, like draw a picture, define variables, those kind of things. So let's read the question first. And I hope you can get excited about this because honestly, if you've been following along and the calculus seems okay, like we're ready to use it. Like this is cool stuff. We can actually do something real with it. So anyway, a farmer here. We've got a farmer. He's got a bunch of fencing, 300 or 3,000 feet of fencing, and he wants to create a pen, and he's going to put it next to a river so that he only has to make 3 of the walls, right? He's going to use like the river as one of the walls. And so he wants to use all the fence, and he wants the biggest fence. So what height and width would maximize the area? So let's slide back up to the steps here, and we'll do the first several things. Let's define the key variables, step 1. Okay, we'll do that. And then we will draw a picture, and then maybe we can come up with the objective function. Okay, so let's do those 3 things right away. So I'm going to start by drawing a picture just in case anyone's confused about what's going on here. It's like we have a river over here on one side, and this farmer wants to build a pen like this, right, with his 3,000 feet of fencing, and we're calling the height and the width of the pen would be the sides. For some reason in my notes I changed height to length, and I can't remember why. I don't think it really matters though. So the height we'll call h, and so let's let h equal, I guess height just feels like it sounds weird. I'm going to change it to length. I think that's probably why. I'm going to change the word height to length. So let's let L equal the length of the pen. And W will be the width. Doesn't really matter what we call them, right? But for some reason, I think height just feels like it's like off the ground to me for some reason. So let's label the sides. So we'll say W is the shorter side, and there's 2 of them, right? And then L will be the one that you only have 1 of, right? So we only have 1 of those sides because the river's on the other side. Okay. And the goal here is to find the biggest area, right? Maximize the area. And so our objective function then is to maximize the area. If you slide back up, objective function is the thing you're trying to optimize. And so we want the max area, right? That's the goal of the problem. And we know the formula for area. That's an easy formula. Oops, if I can spell area correct, that'd be good. So it's just length times width, right? And so this is our objective function. This is the thing we want to find the max of. We want to find the max of this, right? So that's the problem set up. Thoughts? This is a river over here. I don't know if that's clear. Kind of looked weird for a second. Now it's a river. Does that seem okay? We've done the first 3 steps, right? We drew a picture. Always helpful if it's not a simple problem where it's kind of given to us like the previous 2 up above. we want to draw a picture. It's usually helpful. We defined the variables. We wrote down the function we want to find the max of. Is that okay? Any questions about that setup so far? Let me open up the chat here. Okay. So, finding the max just means taking a derivative, finding critical points, like the things we know how to do, right? But in this function, there's two variables currently. There's an L and a W. And everything we've done so far only has one variable, usually X, for example, right? So we don't really know about like taking derivatives of two variables. How does that make sense? And so let's go back to the instructions here. And you can see that the next couple steps are to figure out if there's any constraints, which we do have. And then we use those constraints to write the objective function with just one variable. Because we currently have two, L and W. We wanted to just have one so we can take the derivative. Because then once we have that, we can just find the max using calculus, right? And just double check our answer, make sure it sounds reasonable. And so do you see what I'm saying here? We currently have two variables, but we're going to use our constraint to rewrite it in terms of just one. And so our constraint in this case is that we have 3,000 feet of fence. Oops, that's not what I wanted. And remember, let me just remind you what the constraints were in the last examples. Both the constraints in the previous examples up in the black right there, where we just wanted the variables to be positive. That was the only constraint we had. There was nothing big about that. And we also want the variables to be positive here, but we also have this added constraint of only having so much fence, right? So the constraints are, first, we need both L to be actually bigger than 0, right? We want to have a fence. If they equaled 0, we wouldn't have a fence. And so we want them to both be positive, actually. And we only have 3,000 feet of fence. And so ideally, we would want to use all of it, right? Why wouldn't we use all of it? And so we want the perimeter to equal 3,000. Right? That's a constraint. We want that thing to be big as possible, so long as when you add it all up, you get the materials we have. So this tells us our constraint. This tells us that when we add all the sides, and there's two W's, only one L, we need that to be 3,000, right? In other words, L plus 2W equals 3,000. And so this is like the constraint equation, you could call it. It's how we relate L and W. That's a W. Let me rewrite that so it's a little bit better looking. That's a W. And it's how we can take one of the variables out and replace it with the other one. Let me pause here and see if that looks okay. All right, so just to be clear, what we're about to do, we're going to solve for one variable. It doesn't matter which one. L is the easiest one to solve for, so I'm going to solve for L in terms of W. So that we can plug it into the formula, right? So just kind of looking ahead here. Well, let me just do it and then we'll look at it. So let's do that. So let's solve for L. Just subtract 2W to the other side. So we have L equals 3,000 minus 2W. And then we can take this and substitute it into the area formula above. Because then we'll only have W's in there. All right, so let's rewrite that. So let me switch colors here because we're kind of doing something different. Looks like my internet slowed down there for a second. I will pause. Could you hear me talking, or is I cutting out there?
Couldn't hear you for like 5 seconds.
Oops, it looks like my volume's way down too. Hold on a second. Jimmy, repeat something there?
We couldn't hear you for like 5 seconds.
Okay, so what I was just saying is we just took the area equation that we started with up here. Right, we had this area formula, and so we're just rewriting it, but we're going to take out the L and we're going to put in that expression for L. And so what I had said was this is like a composition of functions thing, right? You're taking out the L and replacing it with a different function. So that ends up being this then, right? Here I am taking out the L, and then I'm going to put that expression right into it. And now it only has W's, right? And we can distribute the W through there, and it becomes this. And this is a really easy thing to find the max of, right? This is the kind of thing that just takes one derivative, super easy to find the max of this. Right, but now it only has one variable was the point. It only has W's, not L's and W's. Like, what do you do there? If you want to take a derivative, what's the variable do you use? We don't know how to do that. Now there's only one variable. It's an easy power rule quadratic, easy to find the max. That's the hard part, I think, because at this point, I haven't finished grading the test, so I don't know exactly how well people understand this. But if you understood the things on the last test, then you get how to find the max of this, and so that's not going to be the hard part. The hard part's setting up the problem, defining the variables, figuring out what we want to do, and then getting it to just have one variable. So this is the hard part. So I'd like to just pause here. I'm just going to kind of rifle off the answer here in a second, but I want to see if there are questions about this harder part. It's just going to be 3000 W. I'm sorry, 3000 minus 4W. Right, and we want that to be 0. Right, we're just finding the critical points, and then we're finding the flat spots, and then we'll classify it. So we can pretty easily just add the 4W, divide by 4, and you would get W equals 750. Let's verify that it's actually a max. There's only one critical point, right? So if there are a bunch of critical points, we'd want to like test each one, figure out which is the biggest, etc. There's only one. So unless we did something wrong, it's the max. But let's just be sure, right? So let's verify it's a max. Let's verify W equals 750 is a max. I'm going to use the second derivative test. It doesn't really matter, but it's nice and easy in this case, because the second derivative is just a negative number. Right, so this is always less than 0. Let me be more clear. If you tried to plug a number in there, it doesn't change that number. And so this is telling us 750 is a max. Right, because it's concave down.
I didn't really follow along there through that step. Can you repeat that?
Sure. So this implies it's concave down because the second derivative is negative. And we also know it's flat. So it's concave down because the second derivative negative is concave. It's flat because first derivative is 0. And so that implies it's got to be a max.
How did you get -4? Where did that come from?
I took the derivative of the first derivative. So, right, when you take the derivative of this piece, it becomes -4.
All right, gotcha.
Other thoughts? Trying to get the top thing to pop up again. Come on, pop up. Because I want to add another page. I hate when it does this. If I do that. If I do this. Okay. So just to kind of finish it, so the width, 750 is the biggest width. So what's the biggest length? Let's review the question actually. The question is, what's the biggest area, right? What height and width would maximize the area is what that says. So we have the width. Let's find the length. And so we just use the constraint again, right? So we know W is 750. And we know that L plus 2W is 3000. That was the constraint that we came up with. And so we can just plug the 750 in to get the L, right? And that's a feet measurement. And so we've answered the question. What dimensions maximize the area? It's L equals 1500 and W equals 750. If the question was, what is the biggest area? Then we would want to plug that into the area formula. And so let's just figure out what that is. Like if the question was, how big is the largest pen? Right, this is the difference between kind of thinking back to the material that was on the test. This is the difference between finding the location of where the max is, which is an X value, and then finding what the max is, right? Which you always take what you have and plug it back in. And so that's what this is doing. If we want to know the largest pen, we just plug it into the formula. Right, these are both feet measurements, and so when you multiply them together, you'll get square feet, which is an area formula or an area unit. I see this chat question that says, do we have to draw a picture? Do we really have to draw a picture every time? That's how I'm reading that one. If the picture is applicable, then yeah, I'd like to see a picture. If it's not always applicable, the one we do next is not applicable. This is actually the only one I think that we'll look at that actually, a picture makes sense. I think, I honestly think it would be kind of hard to without, if you didn't have this picture here, to come up with this. I mean, maybe not like hard, like yes, it's doable to come up with that constraint without the picture. But when you have the picture, the constraint just follows from that. You just see like, oh yeah, I only have one L side. And I feel like if you didn't have the picture, you might miss that. So, is it the end of the world if you don't have the picture? No, but more than likely you're going to make a mistake if you don't draw the picture. So that's what I would say about that. I mean, if you look at the homework problems, the one where pictures are applicable, they always have a picture, and it's to help you with it, right? And you could kind of think about what it would look like if you didn't have one of those. Other thoughts? I didn't really mean that. Maybe that wasn't intended to be whiny. I wasn't really kidding. I was just kidding about that. Other thoughts? Clarification seems okay. I think there's one that's like this in the homework. It had something to do with fences. I was just looking through the homework to remind myself what was in there today. So follow along with this one. There's all similar to this one. So to check those out. And we can, my goal probably Friday is to, things telling me my internet's unstable. Can you hear me okay?
You're cutting out every so once in a while.
Okay. I don't know, my internet is so patchy lately. got an extender and everything. Anyway, I was just going to say my goal Friday is at least set up some of the more complicated problems. Like look at the picture, kind of do the objective function. Okay, let's do one that doesn't require a picture because those are so hard sometimes, pictures. Oof. So let's find two non-negative numbers whose sum is 9 that maximizes the product of one with the square of the other. So it's a super, it's like a very concise question. One sentence, easy kind of setup. It's it's less interesting than the last one. At least the last one we were at least like building a fence or something. Now we're just finding some numbers. But it gives us another opportunity to use calculus in a similar kind of way. And there's one in the homework that's like this too. I happen to notice this morning as well. So when we're thinking about, let's go to the list. We'll define the key variables. We can definitely do that. We don't need to draw a picture, right? There's not a picture that we would need to draw in terms of numbers. And let's figure out the objective function. So let's do those three things. So it looks like if we want to maximize the product means multiply. And we want to multiply the square of one with the other one, right? And so let's just define two numbers first. So n1 is a number. n2 is the other one. And we want to maximize, right? We want to maximize something, and we're going to maximize a product. So that's multiplication. And then we're going to square one of them is what that says. And so that's how we figure out the objective function. So we want to maximize something. What do we want to maximize? The product. So we're going to multiply something. And we're going to multiply one of them with the square of the other. That's what that's telling us to do. And that'll be our objective function. Let's call it Q. All right. Is that okay? Clarification about the setup so far. We did the first three steps. We didn't have to draw anything, but we defined the numbers. We just wrote down the variables, and then we wrote down the objective function, right? So we want to maximize this thing. So find the max. But we first just needed to have one variable. Right? It has two variables right now. We need to do some kind of substitution to make it have just one. It's okay. Let's slide back up to the instructions real quick. So we did 1, 2, 3. We're going to then determine any constraints. And then we use those constraints to rewrite the function. And then we'll just find the max. Right, so that's the key thing. I think like 4 and 5 are usually the things that trip people up, which is relating the two variables and with the constraints and then getting the substitution part. Those are things that oftentimes confuse people. So anyway, let me know if this doesn't look okay, right? So the constraints here, just one sentence, right? So what's the constraint? Oh yeah, their sum is 9. So that's the constraint. So their sum is 9. That implies n1 plus n2 has to be 9. And so we just solve for one, plug it into the other one. Doesn't really matter which one we do. You could solve for n1 and then plug it in that way, or you could solve for n2. It really doesn't matter. There's another constraint too, actually. I should have wrote that down before this one. What's the other constraint?
Non-negative numbers.
Yeah, non-negative. That's been a pretty typical one, right? And that's oftentimes the constraint in optimization problems is we want positive things. It doesn't really apply in this case, but it's nice that it's similar. So we also want n1 and n2 to be not negative. Just wanted to put that. I wish I put that first because it just kind of gets in the way over here, but that's okay. I'll just box it in. Right, but anyway, we want just one variable. So let's just solve for one in terms of the other one. And so n1 has to be 9 minus n2. Right, this is a nice thing that we can use to substitute into the above function? All right, and then it'll only have n2s in there. You with me? Let's do it. So so we know Q equals n1 times n2 squared. Take this and plug it right in there, and you'll get this. Which becomes this. And now it only has n2s. And it's a cubic instead of a quadratic like the last one, but still not too bad to find the max. I gotta start writing smaller on this stuff. Just looking at my notes from my last class, I was really very easily able to fit this on a page. And now for some reason I just get so large on this iPad. Look at how big that was. It's enormous. Anyway, let's maximize this thing. Questions? This is the hard part. So, I mean, the hard part's over. So, are there questions about that part? We're just going to find the max. All right, Q prime, nice easy power rule. It's just going to be 18n2 minus 3n2 squared. We want that to be 0 because we're trying to find the flat spots. It's a quadratic, so it's a little harder than the last one, but it's not too hard. You can use the quadratic formula if you really want to, or we can just factor out a 3n2, and then it becomes something that's not too bad. Right, we get 0 from this one. Or we get 6 from this one. Now this is one, well, yeah, this is one we have to be a little careful of. I guess, I don't know, we can probably reason through that 0 is not the answer, right? If we want to maximize the product of something and one of the things is 0, you're just going to end up with 0. So 0 is not going to be the answer. But it might be, I guess. And if we didn't sort of reason through that, we might think it's possible, right? And so this is one where we want to classify it. We want to be a little bit careful about classifying. It doesn't matter how you do it. I did the second derivative test last time, so maybe we should do the first derivative test on this one, just so we have some stuff to look at. Right, this is just from the last test, so let me know if this is a problem, but we're just going to test these things in the derivative, right? And we're going to test around 0, and so I'm going to test minus 1 and 1, and then we're going to test around 6, so I'm going to test 5 and 7. Right, so we get like negative, 0, positive. And so this is a max, or a min, I mean. Right? And that makes sense. If you want the product to be as small as possible, make one of them 0, because then the product will be 0. But if you want it to be as big as possible, maybe 6 is the answer. And so let's look at that test. When we plug a 5 in, we get a positive number. When we plug a 7 in, we get a negative number. And so this is, right, flat, increasing, flat, decreasing. This is telling us we have a max. What do you think? And did we answer the question? So the question is, find both the numbers that maximize this. So we found one of them. We can just find the other one by using the constraint again, right? We know we want them to add up to 9. And so if one of them's 6, the other one's got to be 3. And so we can kind of finish this off by saying we know n1 plus n2 is 9, and we know n2 is 6, and so that means n1 is 3. And if we want to know the max value, which is not the question, but sometimes the question might be, what is the maximum value? Then we just plug them into the formula again, right? So the max is n1 times n2 squared, which is going to be 3 times 6 squared, 18 times 36 is 108. So the biggest number you can get where you do n1 times n2 squared, where those two numbers add up to 9, is 108. Is that like earth-shattering? No, but hopefully you get the idea of how this can be useful, maybe more so with the fence question. I like these questions. These are good test type questions, to be perfectly honest with you. I haven't written the last test yet, but if I recall, the last time I did a test on this, I did one of these kind of problems because they're not super involved. You use the optimization thing, but you can just like do a one sentence kind of question without it being really complicated. Anyway, just a hint there. I don't. Maybe I won't do that again, but there's a good chance I would say. Thoughts about the idea? What do you think?
Can you go up so I can see kind of how you did a little one of them, because I didn't really get that.
How far up? Here?
Okay, that's good. Thank you.
Can I clarify anything specifically? Go into details about, I don't know, any of it. Calculus, solving the algebra, anything there? All right. I am going to give you an opportunity to try the last one here. We're going to do it in breakout groups. So if you need to prepare yourself mentally for that, that's okay. Or if you're watching this video later, I would suggest you try this one yourself and then we'll look at the answer together. But this is another one of those problems where it's kind of set up for you. And I think the hard part about this one maybe is the algebra and solving the answer, just kind of thinking about some of the struggles people had with the homework last week. Solving problems like this can be tricky. And so this is a real world example. I took this one from a real paper that talked about, was talking about cows again, I think, right? So it says, Charolais, Angus, and Hereford calves are types of cows, I believe. And so it talks about individual daily milk consumption for these 3 types of calves, and it's approximated by this function. And so the idea is like these t values are days. Isn't that right? It's weeks, actually. And so they're really young. They're between 1 and 26 weeks, so half a year old, between 0 and half a year old. As the milk consumption, right? So you plug in t in weeks and it tells you approximately how much one of these calves would drink in kilograms, it says. Excuse me. So we've got our 2 units, we've got kilograms and weeks, and we're going to do 3 things. We're going to, 1, find the max, or find the age of the calf at which the max daily consumption occurs. So sometime during that period, maybe that kind of goes up and then they hit their max and then maybe they'll start drinking less. I don't know if it may not just keep going up, for example. The second question we're going to answer is how much milk is actually consumed. And the third part is just a conceptual question. Do we think that this is going to be the same value for all these calves, or, thinking about like how much do we trust these answers kind of thing, right? So sort of a no right or wrong answer to that one, just thinking about what we're doing and what the interpretation is. And so again, I'm going to break you up into groups and let you think about this one yourself a little bit. Let me just sort of set it up again a little bit further. So the first question, if we want to know where it occurs, we're going to take the derivative of m, set it equal to 0, and find the critical points, right? You'll find some critical point. Let me just remind myself. I think only one critical point comes out of here. Yeah, this one ends up being a little bit tricky, but we can do this. Oh yeah, this ends up being looking tricky, but not actually being super tricky. So we're going to take a derivative, set it equal to 0. This is the part I want you to discuss, basically, is because the derivative is a product rule, and then solving it is a little bit tricky. And so you'll do that, and you'll get one critical point, t star. And then the second question is just plugging it into the function. Right? How much milk is actually consumed is just going to be the function output at that critical point. And so I'd like to spend just a few minutes on this. Let's then say maybe 10 minutes, and then we'll go over the answer. And then we'll finish off. This is the last optimization page. So these are hopefully preparing you for the homework. We'll do a little bit more on Friday, but then we're going to move on and look at the next topic at the end of class today. Thoughts about anything before we think about that? All right, that's a product rule. This is a product rule because there's a t right here, and there's a t in the exponent. And so thinking about what those two, what the derivative is one of the things I'm trying to get you to do right now in these breakout rooms. All right, we'll just spend a few minutes on this. Call me in there if you need something. I'm going to, again, maybe 11:50, I'm going to call everyone back. I'm going to try to run through these breakout rooms, but let me know if I can clarify something. It'd be good if someone would take control and open up the whiteboard and at least get the derivative written down together and talk about how to solve it. That's what we're going for here. Okay, let's do that. All right, welcome back, folks. So I don't know how far you got in that. I was sensing I didn't make it around all the rooms, and I was sensing in the ones I did get to that there's some confusion in this one. So, so let's look at it together. So I've written down sort of the first part of the sort of this far, but know if this doesn't look okay. So it's a product rule, right? And so the t part, the t raised to the decimal, is just a power rule. It's a weird power rule, but it's a power rule. And so I'm writing down the power rule right here for that piece, right? Just bringing down the power, subtracting 1 off the power. You kind of ignore the 6.218 part. That's just a constant multiple, right? And then the right-hand piece is doing the derivative of the e to the x part, except it's a chain rule. And so you end up doing the derivative of the inside piece times the original exponential part. And together it's a product rule because you have the plus in the middle, right? F prime g plus fg prime. And so that's all I've written down here. And then I just, I multiplied 6 times 6.81 times 0.24 gives you the 1.52. And then I subtracted 1 off the power to get the minus 0.7 part. Let's see here, what else happened? Oh yeah, and then 0.28, those two things multiply to give you this piece. Anyway, most people I'd talked to, I think, had gotten this far. But are there questions about the derivative? This one's weird because of the decimals, obviously. But hopefully you can see what I'm saying there. Can I clarify something? Does that look all right? So then we want this to equal 0 because we're trying to find the max. And that's where I found that people were really confused. But are there questions? There's not questions about the derivative part? So think back to every other time we've had an exponential and we want it to be 0, right? We always factor that thing out. And that's the same thing that happens on this one. We factor out the exponential, and then we get something in the middle that we can set equal to 0. Oops. These decimals are throwing me through a loop, just rewriting them. Right? And every time we've done this, we always say, oh, well, exponentials are never 0, and so we don't get anything from that. And it's the same thing, right? So the exponential just kind of gets out of the way, and then we want this inside piece to equal 0, right? And so it's still tricky, though, because it looks like this, right? The t has a negative exponent, and so it's like, how am I going to solve this? And I agree, this totally looks funky. But when you just make one move, like, a nice thing happens. So again, I got kind of caught up, but is there anyone who has an idea about how to solve that? What do we always do if we have we've got this t in the denominator? How do you get?
You have a 0 in the numerator.
I'm sorry, say that again. Oh, yeah, so you're talking about trying to solve a fraction. Yeah, so if we had something like a over b and we wanted that to be 0, we want the a to be 0. And that's true, but we don't have that situation because the t is in the denominator, actually, and there's nothing in the numerator that's a t. So I'm sort of thinking about, like, what if we had the problem 1 over x equals 6 or something? Like, how do you get variables out of denominators? That's the sort of technique I'm thinking about.
Cross multiply.
We could cross multiply, and we could actually, you're right, we could cross multiply on this one. Let's see, do we want to do that? Sure, let's go ahead and do that. It's a great idea. So let's add that thing to the other side so that we can cross multiply. All right, so 1.52 over this funky t thing equals 157 to the 0.242, and that's like over 1. And so if we cross multiplied, these two things multiply, and these two things multiply. Let me just slide that over so I can just do that right next to it. All right, so cross multiplying would end up being 1.52 times 1 equals 6 to the 0.758 to the point. I keep forgetting to write the 2. And this is like the answer, because when you add those exponents, because that's what you do in this situation, you add the exponents, right? It just equals, you get t, and you get t equals 1. I left my coefficient off though, I'm sorry. I forgot to rewrite the 0.157 part. All right, this had a coefficient 0.157. So we're almost there. So we have 1.52 equals 0.157 t to the, add those things. And those things happen at equal 1 when you add them together. Right, so we're like right at the end. Just divide by 0.157. And so we get t equals 1.52 over 0.157, which I think is 9.68. Remind myself what the questions are. So find the age at which the daily consumption, the max daily consumption you can serve. So this is the day that it happens, right? Or the week, I guess, technically. The age. So this is the age at the max consumption. That's number 1. Question 2 was how much milk is consumed? And so if we want to know how much milk is consumed, just take that max day and plug it into the milk function, right? So just do m of 9.68. And I also did that ahead of time. Let me just remind myself what the function is. So this is, 6.28 times 9.68 to that weird variable, or I mean decimal. It's supposed to be a 2. Okay, this is messy because it's a real function. This actually approximates. Dairy farmers might be like using this function to figure out how much milk they need produced for their calves, for example. So yeah, it's not nice. You get these weird decimals. Right? So it ends up being approximately, let's see, what did I write down? About 8.5 kilograms. So when calves are about 9.5 weeks old, they will eat or drink 8.5 kilograms of milk a day. And that's a max. So they're kind of leading up to that day. So, if you're a farmer, a dairy farmer, at 10 weeks, you want to make sure you have your most milk available. And it'll be decreasing after that. I think I'm going to leave that one right there. Questions about optimization things? We've seen, 5 examples. 3 of them were just kind of like quote unquote normal max min problems. 2 of them were required a little more ingenuity. But hopefully you can kind of see how we can start using calculus to do interesting things, find meaningful values, right? Okay, what do you think?
I just have a quick question, Professor.
Yeah.
Since there was only one critical point, you don't need to classify it, right? Like the previous one with the 0 and the 6.
Yeah, I was sort of wondering if I should have done that. It's usually a good idea too. I was just kind of skipping over that one for the sake of time more than anything. If I had a little more time
Okay.
here, because I wanted to look at the next page, I might have just classified it for the sake of classification. But yeah, there's
Okay.
only one of them. So unless we did something funky, it's going to be the max.
Okay.
Yeah, thanks for clarifying that. Other things? Oh, what about the third question is this reasonable? Again, just for the sake of time, that's the sort of thing where it's like, well, Is every single calf going to drink that exact amount? No, right? It's an approximation. It's based on data, but some are going to want more or less than that. But this gives you an idea of how to prepare, is sort of what I was getting at there, right? Like, don't put all your eggs in the basket and say like, well, they only need this amount because they might need more, but it gives you an idea, right? That's the whole point of these math models, is like help you prepare, make projections, think about what's going to happen before it happens. But understanding that's not completely accurate is also important.
Questions on. So people sent me some emails. People were interested in looking at 2, 4, 6. This is number 7. Doesn't have a number, but it's number 7 and 8. And I'm not going to like do all of them, but I'll help us get started and help us think about how we can at least start these problems. And you can let me know if there's more you want to look at moving forward. I know like a decent number of people haven't started these, so I don't want to go too far into them. So on this first one, the reason this first one's confusing is because it's got a lot of variables in there. So this equation, like it says in the problem, it tells us the speed at which a fish swims. And so V is the speed, right? Relative to a bunch of other inputs, right? So it's got, let's see, it's got L, which is the distance. It's got U, which is something that I'm not seeing the definition of. The current, is that right? Yeah, so I guess it's the current. But I think the confusing thing in this is what do you actually do? Because it's all variables, right? And so the question says, I'll get my notes out on this just so I don't lose track of what I'm talking about. It wants us to take a V derivative, because you can see V is the variable, and it also wants to know determine the value of V that minimizes E, right? So this is telling us to take a V derivative of E, and then we will set E prime equal to 0 to find the critical points. Right, and then we'll figure out which is a min. Although, yeah, we should make that. And we'll classify them. And so again, I think the confusing thing in this is there's no numbers other than the cube and the exponent. And so that's usually what trips people up on this. And the thing that is kind of key, which is a little bit related to what we're doing in class today, but only tangentially, is if we were going to take the V derivative of some non-V variable like X, for example, we treat it as a constant. So when you write d over dv, it says, hey, the variable's V, and we're going to differentiate V. And so if you're differentiating X with respect to V, it just becomes 0 because it's like treating it like a constant. In other words, it's not a V, and so you don't apply the derivative rules. You instead apply the constant rules to that one. And so, you know, the derivative of X would be 0 in that case. Or let's say we had an example like we wanted to take the derivative with respect to T. Should I do T? Yeah, let's do T of like 2x y t squared, right? So there's a bunch of variables in there. There's also a number, but we're differentiating with respect to T specifically, right? If we're doing that, we ignore the 2, the x, and the y, and we just differentiate the T part, because that's the variable we're being told to differentiate, right? So this is kind of extending this to future classes a little bit, getting us to ignore the things we're not differentiating, right? So if we differentiated just the T part, this would become 2xy times 2t, right? And then we can multiply the 2's and get 4xyt, if you catch my drift there. And oops, so that's the kind of thing we want to be thinking about in this problem. When we differentiate with respect to V, we're going to ignore the things that are not a V. And we're just going to pretend like there's a number in there. So that's my general setup. I'll do a little bit of this one at least. Maybe we could do the whole thing. I don't know. Should we do the whole thing? I don't know. Let's start it at least. Are there questions about what I'm trying to say? Sort of the setup. Okay. So I'm going to add another page here just so we don't run out of room. Let me rewrite this problem. So the problem is E equals AV cubed L over V minus U. So I just took the thing that was out front and I put it in the numerator. Is that okay? Everyone see that? This thing is multiplying and it just goes into the numerator. And so it becomes this. And I wanted to do that because now it's a quotient rule. Before it would have been like a product rule and a quotient rule. And so we're going to do d over dv, and we're going to treat a, l, and u like constants. And if it helps, you could just put numbers in there if you wanted to, and then maybe it's less confusing. But then when we do that, when we think about it like that, and we do d over dv of e, it's going to be a quotient rule. Right? And maybe I'll at least write down the first step here. You can let me know if you want to see more, but when we do the quotient rule, right, that it becomes this. F prime, how much detail do you want to see? F prime G, right? So see how I differentiated this thing only into this and the 3? Right? I ignored the A and the L. I just brought down the power, subtracted 1 off the power. So that would be the numerator, F prime G minus F. And then G prime is just a 1 because we're only differentiating the V. How's that derivative look? I feel like that's the most confusing part here. We're treating everything like a constant except the V. So maybe I'll leave those highlights, right? So this thing turned into this and this. And then this thing just turned into the number 1. And the U just went away because it was a constant and it became 0, right? Should I say some more about that? We'll see what's going on there. Okay, maybe just in the interest of algebra, I'll take it a couple steps further. So we want this to equal 0 because we're trying to find the critical points, right? And so we take the numerator and we set that equal to 0. And so we do the numerator equal to 0 because it's a fraction. And the numerator ends up simplifying in these kind of steps. It ends up being, how many steps should we show here? So I'll just say after simplifying, it becomes 2ALV cubed minus 3ALUV squared. And we were solving for V, right? So how do we solve something like this if we're trying to get V by itself, right? I'm highlighting the 2 places where V is located in that expression. What would you think about doing? We've seen a bunch of problems that look similar to this. Don't let the extra things confuse you. Those are just like coefficients. Right? If you had numbers in there, it'd just be like something V cubed minus something else V squared, right? Thoughts? What should we do when you see those 2 terms like that? So these 2 things are being subtracted, so we can't combine them because they're not like terms, right? This is a V cubed, this is a V squared. The thing I'm trying to point out is if we want to get V by itself, you can factor out a V squared. right? Again, we're trying to solve for V here. And so that was helpful because now the inside piece only has one V, right? We still want this to be 0, so equals 0. And so we can just set those things equal to 0 separately. Actually, I could have factored more out, right? I could have factored an A and an L as well if I wanted to. It's not super important though, so I'm just gonna leave it like this. Right, so this one could be 0, so we get V equals 0, that's a critical point. Or this piece equals 0. Right, if you want to get V by itself, just divide that other stuff over to the other side, except this should be a U, just to be clear. This is a U. And so V equals 3ALU over 2AL. The A's and the L's cancel. And we just get 3/2 U. Or you could write it as 3U over 2 if you want. So this is the other critical point. Trying to read the problem again. Minimize the energy. Yeah, it's not super. Anyway, questions before I say something else? We got those numbers? That's a U. My U's are terrible right now. That's a 3U over 2. So what's the answer? The answer was, or the question was, what value of V minimizes energy? And so the question is, which is the min? How do we figure that out?
A test.
Yeah, so we could either use A, either the first or second derivative test. Although to be perfectly honest, that's going to be a little tricky because we don't have a lot of numbers in here. And so maybe we could plug numbers in to the derivative and get some values. But I think we can probably just reason which one of those makes the most sense. And I was trying to, I wrote in my notes that V equals 0, this one right here, violates the constraints. Because if we look at the problem, this I think is the key thing here, which is that U has to be less than V. And U is some non-negative thing, right? So V has to be positive then. Right, and so this can't be possible because it's not positive. Right, the fish is swimming, and so if it's swimming, its speed can't be 0. That's another way to sort of think about it. So first derivative, second derivative test is fine. That's a good way to think about it. Although I just, full disclosure, it's going to be tricky. Or just use reasoning about constraints. All right, so we pretty much finished that one off. So this is going to be the min. And I think everyone has that same value, that same problem. So it's not like you have to do something different. Thoughts about that one? Clarify anything that we did there? That one took a while, which is fine. You know, looking back at my past notes, I ended up spending a class or period or so in my past classes like looking at these problems. So I have no problem doing that today. Are there questions about this one though? Okay, I'm probably not going to do the next one, but we can set it up. and maybe I would be asking whoever asked this question to maybe clarify what it is confusing about it. So let's read this one. So we've got a civil engineer. They want to estimate the maximum number of cars that can be on a road at a given speed. They're assuming that each car is 20 feet long. Sounds like a constraint. Travels at a speed of s, and follows the car in front of it at a safe distance for that speed. I don't know if that's relevant, but okay. He finds that number n of cars, so n is the number of cars, that can pass a given spot per minute is modeled by this function, right? So n is the number of cars, and s is speed. And the question is, what speed can the greatest number of cars travel safely on the road? How do we want to do that? What's this asking mathematically? What's this saying? Anyone? You want to do this one? Gregor?
It's asking for the maximum number of cars that can travel safely.
Yeah, so how do we do that mathematically?
Find a critical point.
Yeah, so we're going to look at n prime, set it equal to 0, find the critical points. Did you ask this one, Gregor? I can't remember.
Yeah, I did.
So yeah, what was the answer?
But not when I look at it, it's pretty.
Okay. Yeah, I would categorize this in one of the easier categories. None of these are easy. I want to be clear, right? This is finding critical points of a rational function that has fractions in it. So like, there's definitely confusing aspects of it. We've been building up to this it's kind of the peak of, critical point finding, but it is kind of sort of a quote unquote straightforward rational function. And I would encourage you, if you're struggling with finding the derivative and you're wondering whether that's hanging you up, you can always just go to something like wolframalpha.com, or if you just put it into Google, like type this function into Google and say derivative, you can always verify your answer that way. You obviously want to be able to do it by hand, but if you're just concerned that that might be the problem, that's a good way to check. So maybe I won't do this one if that seems okay. I think the next one's kind of similar, so we can look at that one too. Is that okay? Okay. So the next one, no, that's not the one I was thinking of. So the next three, I guess, they're all of the type where you need to make the equation ourselves, right? So maybe I'll just open up the notes real quick and remind ourselves how to do that. So we're thinking about these steps, right? Defining the variables, drawing a picture, coming up with the objective function. Those are usually the three things I try to do together. So let's do those first three steps of, this problem. This problem. And then we can see if we want to keep going or not. So this is similar to the example we did, right? So a guy's building a fence. We did an example like that in class. The difference between this one is that it's a different shape, right? So the ramp chair has a certain number of square feet that it wants to enclose. And they're describing what it looks like, right? So it's a rectangular field, but divided in a half with a fence down the middle. And so let's draw a picture of what that looks like. Maybe like that. Although it's not clear if the line's supposed to be like that or like this, I guess. But I don't think it really matters. But the key thing is that it's rectangular, right? So if we start labeling things, we know like the three things going down the middle are the same size, for example. So we can label like X, 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 for example. And then the sides might be Y, Y, or something like that. And so we could say like, maybe I should move this up to the top. Oops, I moved my highlight as well. That's okay. So we can say, what were you going to say? I was going to say X is the width, Y is the length, and the objective function is to minimize the total amount of fencing, right? Subject to some constraints. So what's the total fencing? Looking at the variables we have, what's the total fencing?
2 million square feet.
So that's the area. So someone online said 2 million square feet. The 2 million? 22 million, yeah. So we want the area to be 2 million. But the total fencing is like a perimeter thing, right? So we want to minimize the total fencing, which is 3 X's and 2 Y's. Really needs to be clear that that's what we're trying to do here, right? Total fencing, minimize it, whatever it says, whenever it says minimize or maximize this or find the most or find the least, that's the objective function, right? So when it says minimize blank or maximize blank, that's the thing we want to be writing down. So minimize total fencing. Okay, I'm looking at my picture. What's the total fencing? Well, there's 3 X sides and 2 Y sides. So that's how I got 3X plus 2Y. Is that okay? The 2,000 square feet part is the constraint. And so we want to minimize that value. Okay, well, what's the minimum value of that? 0 is the minimum value of that. If you have 0x and 0y, that's as small as that could be. Or if you made them negative, it'd be even smaller, right? But when we put it in context, that's when it starts mattering. So we don't just want this to be small. We want it to be small while being 2 million square feet. And so that's the constraint. You need 2 million square feet of fencing, right? And so what's the area of this thing? This is an area formula. In terms of the X's and Y's, what's the area of that enclosure?
Y times X.
YX, yeah, base times height. Right, and so we need X times Y to be 2,000, or 2 million, excuse me. 1, 2, 3, 4, 5, 6. Right, the constraint is how we get rid of the variable that we don't want to be dealing with. Because currently, if we were going to try to find the minimum of this fencing equation, it's got an X and a Y. We don't know how to differentiate things with X's and Y's. So we use this relationship to get rid of one of those variables. Remember how that worked in those examples? Just to kind of flash back to the notes. Right, we did that. Let me just look at the fencing example we did. Right here is a fencing example. We had a similar thing where, hey, we want to find the max of this thing, but it's got an L and a W. And so we look at the constraint, solve for the constraint, and then rewrite the thing that we wanted with just one variable. And so we're going to do the same thing here. It's just a different formula for the area, for the objective function, and it's a different constraint. But it's the same idea. So, going back to this example then, we want to take x times y equals 2 million and use that to substitute out one of the things from here. Right? So this thing is going to rely on this equation in this way. We could say, it doesn't matter which one we do, we could say y equals 2 million over x. Or you could do x equals 2 million over y, right? Really doesn't matter. But then you take that value and you plug it back into the equation. So we know we want to minimize 3x plus 2y, and I know that this equals y. Right? And now it's something that only has one variable, and we can find the minimum of that. So I would like you to finish that one. I don't really think I want to do it for you, but I think it's similar to one of the ones we looked at. Thank you. What is it similar to? It's similar to solving the equation that comes out of there is going to be similar to solving this equation. Right? It kind of looks like this. Because you have a t in the bottom and the t in the top. Right? We have that right here. Because you got an x in the bottom and an x in top. So it's going to be similar to this, to solving from that equation. So you can follow along with that one is what I'm trying to say. The setup's the important part. If this is a test and you got this far, you get most of the points. So can I clarify something about it? Okay. I will put these all in the drive, of course, to get you, so you can reference them later. Come on. Okay, this is number 7. I forgot to screenshot the number. Actually, there's, oops, someone asked a question. So then we would take the bottom equation in green. Let me go back. For some reason, my iPencil is having some issues here. Geez, okay, sorry. So we take the equation in the bottom in green, set it equal to 0, and find the min. No, that's not how we find minimums. How do we find minimums? We take the derivative, we set that equal to 0. That tells us the critical points. Then we classify the critical points. Right, similar to the one we just did a second ago, or this one here. Right, we took a derivative, we set it equal to 0, we found the critical points. Okay, let's keep going. Let's set this one up. Love this one. But this one looks really complicated, but they're actually just trying to like walk you through it step by step and not just, you know, like the last one was just do the whole thing and then tell me the answer. This one is first write down the constraint, write down the objective function, substitute them. So it's getting you to do it step by step. So don't be scared of this one. And it's an interesting problem, right? So it's saying, okay, US postal regulations, here's a hypothetical package. The girth plus the length can't exceed 108. And then it tells us the girth is the smallest perimeter of the smallest side, I mean. So what that means is, if this is our package, what's girth in terms of those variables? It's the perimeter of the smallest side. So X is the smallest side. What's the perimeter of that side? 4X, right? There's 4 sides on that small side, right? The perimeter of the smallest side. And so what this says is girth, what is it? Girth plus length can't exceed 108. Let me make sure I don't miss anything. I would do this one ahead of time just to make sure it's good. Yes, okay. So, it's walking us through it though. So let's just do it step by step. The first question says, what's the formula for the volume? Oh, because the question is, what dimensions maximize the volume, right? And so if we want to know the dimensions that maximize volume, we should write down the volume equation. What's the volume of this thing? How do you do the volume of a 3D thing, you know? Yeah, you multiply all the dimensions together, right? So it'd be x times y, or x squared y, right? That's the volume of this thing. So that's our objective function. But okay, ultimately we want to be able to figure that out without it walking us through it like this, but hopefully that makes sense, right? We want to find the largest volume, so that's volume. And then it says, okay, well, we can't find, we're going to minimize this in a second, or the maximize it, I mean. But like it says right here, the problem tells us that the parcel's length plus girth can't be more than 108. And so if we want to maximize volume, like it says, I'm just reading this paragraph. If we want to maximize volume, we assume that we actually need the girth plus length to equal 108, right? So it has to be less than that, but we want the volume to be as big as possible. Let's hit the biggest mark, right? So what is the relationship that represents that? So we want girth plus length to equal 108. And so that means girth, which is 4x, plus length, which is y, has to be 108. And so that's our constraint. Are there any other constraints? There are other constraints. What are the other constraints that may help us later? Y has to be not negative. What else can't be negative? X, right? We can't have a non-existent box. We want a box. If they were 0, we wouldn't have a box. If they were negative, we'd be in some alternate dimension or something. So we need to have positive numbers. And this is helpful because if we get a bunch of critical points and some of them are negative, just forget about them, right? That's why that's helpful to kind of check that with your understanding. Okay, and then it's saying, okay, well, let's solve this in terms of y. And so just subtract 4x to the other side. And then it wants you to substitute it into the volume equation, right? So we used to have x squared y, but what we just did is we solved this for y. And so we can take this piece and put it into the y, right? And then it would be x squared times 108 minus 4x. And we want to find the max of that. And so that would be a product rule, right? If we took the derivative of x squared times 108 minus 4x, this would be a product rule. Can we do something to make it easier than a product rule? Yeah, just send that x squared through and write it as 108 x squared minus 4x cubed, and then it's just a power rule. Right, so just that kind of thought process saved us. The product rule wouldn't have been horrible, but now it's just an easy power rule, right? And we're going to find the max, or you're going to find the max. Sort of the question before that involves doing v prime equal to 0, classifying the points. What do you think? Anything at all? Anything I can clarify there at all? Feel okay finishing that one? Okay. I think the last one is the hardest one. And it's the hardest one because it involves some trig stuff. Or at least some triangle things. Anyway, this is definitely the hardest one. I'd like to at least, we'll set up the objective function again. Let's just at least do that. And this is one that a picture would be really, really helpful for. So a fence, which is 3 feet tall, runs parallel to a building 4 feet away from the building. Let's draw that picture first. So we've got a building. I'm going to draw the picture down here, and then I'm probably going to go over to another page. So we've got some building, and it's parallel to a fence that's 6 feet tall. This is my fence. And it says it's 4 feet from the building. then we want to take, this is like a super classic problem, by the way. I don't know if you've ever seen one of these before, but pretty much every single optimization textbook has a problem like this. And so we want to put a ladder against the building that gets over top of the fence, right? So we want to do something like this, where this is my ladder. And the question is, what's the length of the shortest ladder that will reach the ground, that will get over the fence to the building, right? Because if the ladder is too small, it's going to hit the fence is the idea. With me on that setup. So, you know, when you see problems like this, it should be just screaming right triangle kind of things, right? We're making a triangle kind of shape there, and it's actually two triangles. So if I simplify this picture a little bit, it really looks like this. Right? We've got a right angle here and here. We want this side length. We want to minimize this side length L, and we know these two dimensions. I'm going to continue to label this, so I'm going to move it over here a little bit. And so let's call the length of the bottom triangle X, and maybe I'll move this one so it's a little more clear. And so if we want to know the length of the entire bottom, that's not what I wanted. What's the length of the whole bottom of that triangle? X plus 6. Okay, that's a good setup. I'm going to label the height of the building Y. Does the picture look okay? Add another page here.
Are the dimensions the same as in the column?
Yeah, I think so. They're going to be different. So the one I pulled up had 6 and 4. Oh, it's supposed to be 4. I'm sorry. That's what you're saying. Sorry about that. Does everyone see that? Those 6s should be 4s. They're actually, you know what I'm going to do? I'm going to change that 4 to a 6. Everyone has different numbers. Does everyone see that? I'm just changing this number to number 6 just so it matches up with the diagram I just drew. Okay, does that seem okay? All right, so anytime you have a right triangle, there's two things that come up a lot. There's 3 things that come up a lot. Either SOHCAHTOA, a squared plus b squared equals c squared, right? Pythagorean theorem. And the third is similar triangles. Are you familiar with similar triangles? If you have something that looks like this, like the situation we have, it's like you have a big triangle and then there's a little triangle inside of it, right? And if they're labeled like this, let's say let me just zoom in on this triangle. If this one is labeled A and the whole thing is D, and let's say E, B, then this relationship is true. You can compare sides in the big triangle and then compare sides to the little triangle. For example, you can write something like E is to A as B is to D. This is called similar triangles. And to be perfectly honest, this is the kind of thing that I needed a refresher on when I started teaching this stuff, because it's been so long since I've seen it before. Do you remember that kind of thing? So E and A, notice E and A, like E is the same. What I'm trying to point out here is E and B are kind of like the same side lengths. They're the same sides, right? They're both like the right-hand side of the triangle. And then A and D are both the bases. And so that's what lets us compare them like that. You're comparing the same right side to the bases. Does this ring a bell at all to people? Or is anyone like, yeah, it's like a high school, it's a thing that you learn, I think, in a full-on trig class, although I'm not, it's been a while. And it's not the kind of thing I review in pre-calc if you've had pre-calc with me. So anyway, those are the three things that always come up with the right triangles. And so I just wanted to write the three things down. And we're going to use two of them in this problem because we want to be able to relate the sides, because that's how we're going to maximize or minimize something, right? And then we have some constraints. We have constraints like we needed to get over the building, right? We want to maximize the ladder. So we have these things that we want to make happen. So that's sort of the general setup. I'm going to keep going with it, but are there questions about the triangle stuff? Check my time here. Okay. So seem okay? All right, so we want to minimize, right? Minimize. What is the length of the shortest ladder? And so our objective function then, we want the shortest ladder. And so what is ladder? What's the equation for ladder based on our picture? Yeah, we want to use the Pythagorean theorem. So we want to minimize the ladder. And the ladder, looking at the picture on the top there on the second page, or on the first page, I mean, is a squared plus b squared equals c squared. So it's y squared plus x plus 6 squared. All right, this is Pythagorean theorem. You don't have to, but it might help later. At this point, we're not ready to do any derivatives though, because it's got an x and a y. Oops. Right, we have an x and a y, and so we need to get rid of one of those is the next step. And that's where the similar triangle thing comes in. So let me clarify that and see if there are questions. This is the only thing we're doing today, just by the way. We're just gonna work through this, hopefully make it make some sense. I'm happy to give you more time on it too if you need it. But anyway, what we need to do is need to write one variable in terms of the other. That's what we've done every problem so far. Instead of having an x and a y, we need just an x or just a y. And so that's where the constraints come in. Or in this case, the similar triangle thing. Are there questions about the Pythagorean theorem? Does that seem okay? I'm gonna zoom out a little bit so we can maybe keep looking at this. Why wouldn't it zoom out? I'm having such a hard time with this today. I'm not gonna be able to zoom out? Okay, that's fine. So using similar triangles, similar triangle property above, looking at the picture, tells us, remember, E to A equals B to D. So that would be 6 is to X as Y is to X plus 6. Let me write that down. Let me do it in the same way. So I'm going to use this property on this triangle, right? So E is side 6, A is side X, B is side Y, D is X plus 6, right? So we end up with this relationship. 6 is to X as Y is to X plus 6. And that's helpful because that's how we can relate X and Y. Right? We can solve for Y in terms of X or vice versa. Right? In other words, you could multiply the X plus 6 and get Y equals 6 times X plus 6 over X, which is 6 plus 36 over X. And so you can sub into the L equation. Right, this thing is going to go into the Y. And so really what we want to do is you want to find the min of L equals 6 plus 36 over x squared. I've got a pretty crucial error on my screen right now that I just caught, but anyone thinking that I wrote something down wrong? Usually I feel like someone might catch that. Did I do the Pythagorean theorem right? That's what I'm looking at. So in the Pythagorean theorem, a squared plus b squared equals c squared, right? So this L needs a square on it. Everyone see this? I don't know if you can see that. See this thing I just added, the square? Right, a squared plus b squared equals c squared. I forgot the c squared part. And so that also needs to go right here on the last part, which means the thing we're really trying to minimize is the square root of that. So find the min of L equals square root of that nasty thing. Questions about the setup? Anything? I hope that's not just so confusing that you don't have a question, but I'm happy to wait. In fact, I will wait, let people catch up, and then I will say one more thing, and maybe we can look at the quiz. Anything here at all? The only other thing I was going to just finish with on this problem was just, I'm not going to find them in, you can do that, but let's talk about how you do that, right? How do you, so find them in, you're going to set L prime equal to 0, etc., right? But how do you take the derivative of that thing? What is this going to end up being? Like how should we set up this derivative? What kind of rule is it? So what rule? It's a chain rule. Sebastian, I see your question. I'll clarify that in a second. So L prime is a chain rule with the inside function, I'm sorry, the outside function being the square root for x to the 1/2, right? And the inside function being what's inside there. And so to the point or the question before, if you want to do the derivative here, you could either square this out and use the power rule, or it's two chain rules. Whatever you want to do. I'm going to clarify Sebastian's question in a second here, but you'll feel like they can finish this one. What do you think? So Sebastian's question was, where do we get 6 over x? So we're doing similar triangle stuff. So we're doing this idea. Change my color here. we're doing this idea, right? So I did E is to A as B is to D. That's what I did in this situation, right? So I like compared the two right sides, or sorry, I compared the right side to the bottom side in the big and the small triangles. And so that's the same thing that's going on in this example, 6 over x, with our picture. Let me redraw the picture right here. Maybe that would be helpful. So our picture looks like this, where we had 6x, is that right? No, the other way. We had an x and a 6, and then the whole thing was x plus 6. This is y. And so that led to these things. God, I mislabeled it again though. Those x's and the 6 need to be switched. So it's a similar triangle thing, Sebastian. It was this thing right here that I was trying to explain. Let me know if I can say something more about that. Other thoughts at all from anyone?
Where did the x go?
Where did the x go and what?
And 6x cancel over x equals y over x plus 6.
So we solved this equation for y, which became this. And then that simplified into this. Like, is that your question? Like, how did it go from here to here?
But I still don't understand where the x went.
I guess I'm not clear about what you mean by where x went. X is right here. There's an x.
Never mind.
Right? If you want to know the algebra behind that, let's take a look. So if you have y equals 6x plus 6, you can distribute the 6, and then you break it up into 2 fractions. These cancel, and you get this.
Okay.
There's really no need necessarily to do that. I just had him do that algebra when I was working on this one earlier.